Hello all, welcome again. If you did not subscribe to our channel, please subscribe to our channel by clicking subscribe button. And this is a session on high resolution timers. In this session, we'll walk through the forward and a timer made of 6 counters, a crossbar unit, versatile output management, multiple input management, timer A through E, timing units, and 3 timer operating modes available: repetition counter, set or reset crossbar, capture unit, half mode, auto delayed application example, push pull mode, dead time, master timer, external events, external event conditioning, external event management, output stage, chopper, and burst mode controller, fault management, numerous fault management options, and triggering ADC with Hrtim, that is high resolution timer, digital to analog converter trigger, register update, and interrupt vectors, namely 7 vectors and 85 sources, and DMA requests, that is 6 requests and 77 sources, and low power modes, application example, and related peripherals to that. So let's move forward. If you really like this video, after listening to it carefully and watching it carefully, you can go through. STM32H7's HR timer, that is high resolution timer, is a derivative of STM32F334 version in terms of achievable resolution, around 2.1 ns versus 217 ps. Still, it offers the very same features and functionalities, and most of the STM32F334 HR timer ecosystem will be beneficial for better understanding how the timer works. Still, with its 480 MHz input clock, it offers twice the resolution of the STM32H7 general purpose timers. For instance, it is able to generate 14-bit accurate 20 kHz PWM signals and have a frequency resolution of 25 Hz for 100 Hz range PWMs. Even more noticeable, compared with the standard timer, it offers a much higher flexibility for building up to 10 complex waveforms, either timing or event driven, given its features and number of manageable IOs. This is not only useful for digital power conversion, that is SMPS, digital SMPS, solar converters, motor control, but also for general purpose applications. So although we talk about a single HR timer, it is actually made up of 16-bit counters that can either be independently or synchronized, each of them having an independent clock prescaler. It is equipped with a total of 24 compare and 10 capture units and can control up to 10 outputs. Have a look at this. If you see, there is a crossbar, a large central crossbar unit allows to have the output pairs controlled by not only by the related timing unit, for instance timer A for the output CHA1, but also by any external event, the other timing units or the master timer. A total of 32 set and reset events are available per output. So the crossbar is followed by a versatile output management. Here is it. This feature able to interface with any kind of gate driver, program the output polarity, the PWM idle and safe states levels, insert a dead time and or add a chopper modulation. A hardware burst mode controller facilitates the light load management with a built-in pulse skipping mechanism. It also features an ultra-fast and asynchronous fault protection feature independent from the system clock. So we have given in the red block, right? And So on the left corner you can see like multiple input management, left corner. Okay, the HR timer is able to handle 10 external events for dynamically modifying a waveform in addition to 5 fault signals for protecting power stages. The 10 events can be selected among external ones on inputs and internal ones, typically from comparators. The event allow performance of output set or reset to reset the PWM counters or capture external timings. The fault signals are here to protect the power stages and shut down the PWM outputs. The HR timer is also linked with other timers as well as the DMA, ADC and DAC peripherals via internal connection. Let's take a closer look at one of the high resolution timers, 5 identical timing units, that is A through E. It is made of 16-bit up counter with a programmable overflow value to adjust the counting period. 4 16-bit compare units and 2 12-bit compare units are linked to this counter, each with interrupt and DMA capability. A compare event is generated when the counter exactly matches the compare value. Okay. Several compare events can thus be generated during a single period to have the output set and reset multiple times per PWM cycle. The unit embeds all control features for a pair of outputs. It can eventually operate as an independent timer. Yet these options can be controlled by the other timers. So the up counter can operate in 3 modes: in continuous mode, also called as free running mode. The counter rolls over to 0 when it exceeds the value programmed in the periods register or restarts counting if it's reset by an external event. This is the most common mode used for fixed frequency converters or the externally synchronized variable frequency converters. In single shot mode, the counter is started by a reset event and it stops when it reaches the period value set in HRTAM underscore PRXR register. 2 options are available here. In non-retriggerable mode, the counter reset events are discarded if they occur before the end of the counting phase. Typically, this is to make sure an externally triggered pulse will always have the same pulse width. In retriggerable mode, the counter can be reset at any time. In this case, an externally triggered pulse may have an extended pulse if it receives multiple triggers closely enough through. So each timing unit includes a repetition counter similar to the one available in STM32 timers. It allows all offloading of the CPU by decoupling the switching frequency and interrupt frequency. The counter rollover interrupts can be issued every single second, third and up to 256th PWM period, which we already discussed in our previous, but this feature is available both for continuous and single shot modes. In this case, the repetition counter is decreased on each reset event. So set or reset crossbar combines the set and the reset events of the reset events to build the output waveforms regardless of polarity programming. The events may come from the timing unit itself, from other timing units, from the master timer or from external events. The timing unit contains 2 crossbar programming registers per output, one defining the set events, the other for reset events. Up to 32 events can be selected simultaneously. This allows building periodical waveforms with multiple set or reset events per period. The programming registers are shadowed with preloaded registers so that the waveform can be modified on the fly without any risk of having abnormal transient waveforms. So carefully see the figure shown here. Then we will move on to the capture units. So in parallel with compare units, each timer also embeds two capture units. The capture triggers the transfer from the current to counter value into the capture register. This is useful for determining external timings and for the auto delayed mode discussed on the next slide probably. Typically, it offers the possibility to measure the effective duty cycle in cycle by cycle current controlled converter, where the PWM pulse is terminated when the current comparator trips. The capture triggers can be selected from among 28 sources: external events, adjacent timing units, adjacent output waveforms, as well as update and software events. It is possible to simultaneously enable several trigger sources, which is a boon for any of the projects if you start up with. So we have something called as half mode. Is a feature that allows a reduction of computational burden when a variable frequency 50% duty cycle PWM waveform must be generated. This is typically the case for resonant converters, where the operating frequency is continuously adjusted by the control loop while the duty cycle must be maintained at 50%. The half mode operating principle is to have a write access to the period register, triggering a computation and an update of the compare one register to half the value of the period. Let's consider a PWM signal set on the period event and reset on a compare one match. As soon as a new period value is written into the period register, the compare value is also updated to the period by 2 value, so that the output set event will still happen right in the middle of the PWM waveform. This is particularly useful for continuous mode fixed frequency operations, but it can be used in any other mode as long as the period register needs to be accessed. Alright, so after this we'll look at half mode. Is a feature that allows reduction of computational burden when a variable frequency 50% duty cycle PWM waveform must be generated. This is typically the case for resonant converters, where the operating frequency is continuously adjusted by the control loop while the duty cycle must be maintained at 50%. The half mode operating principle is to have write access, isn't it? So this is about auto delayed, which computes on the fly compare value on external event arriving time capture. So a new capture is possible once auto delayed event has happened after counter reset or rollover. Let's have a look at auto delayed application example. Auto delayed mode offers the possibility to have set or reset timings reference to external events and not only related to the internal time base. Still, a timeout mechanism can ensure a default waveform when the external event is not present or disappears. You can check in this particular figure. The HR timer computes a new compare value on the fly based on external events arrival time captured in a register as soon as the event arrives. The delay versus the expected event is programmed in the compare register, but the compare event is inhibited until the capture is triggered. You can check that arrow mark there. When the timeout safety mechanism is enabled, the capture is forced when the counter equals the timeout threshold defined in the compare 1 or the compare 3 value. A new capture is possible once the auto delayed event has happened or when a new period starts. Let's quickly move on to the push-pull mode. The requirement is to build a waveform as follows. The output must be set on compare one match with a fixed timing versus the counter start value. Here two clock cycles, isn't it? The output must be reset 5 cycles after the external event falling edge. The output set occurs when the counter is equal to 2 and matches the HRTIM underscore CMP 1 or register value. The HR timer TIM underscore CMP 2 or register is equal to 5 but is ignored until the external event falling edge occurs. The current counter value is 7. It is captured in the HRTIM underscore CPT 1R register and added to the HRTIM underscore CMP2R preload value. This yields an effective compare 2 value of 5 plus 7 equals to 12. When the counter matches this compare 2 value, the output reset event is finally generated. The 5 cycles after the external event falling edge, the uncertainty of 0.5 cycle in the figure is the normal latency due to the capture signal resynchronization. The HR timer's push-pull mode simplifies the management of push-pull and resonant converters. So in this figure, two identical waveforms are programmed on output 1 and output 2. The push-pull circuitry disables the outputs every 2 cycles out of phase so that the signals can be built using a single compare value to set the PWM duty cycle. This is also possible without using the push-pull, but it would be at the expense of other 2 compare registers and a large CPU burden. Finally, it must be noted that it is possible to unbalance the signals and generate asymmetrical waveforms. For instance, a PWM using compare 1 for output 1 and a PWM using compare 2 for output 2. A dead time can be inserted after the crossbar to generate quasi-complementary signals on the 2 outputs out of a single reference PWM. This allows safe driving of all topologies based on half bridges including full bridges and 3-phase inverters. By inserting a dead time during which the 2 power switches are turned off, this avoids any problem of cross conduction and shoot through. The dead time value can be individually adjusted for both rising and falling edges asymmetrically to handle any kind of driver or propagation delay. You can see in the figure, na? For very specific cases, it is even possible to program a negative dead time and have some controlled outputs overlap. The dead time registers are preloaded so that the timing can be adopted in real time without any risk of spurious transitions, which we discussed earlier also in general purpose timers. This is typically used for adaptive control to optimize the converter efficiency. Last, for function safety purpose, it is optionally possible to write protect the value or the signs of the dead time with specific control bits. So we have master timer comes with 5 timing units using the same architecture. Its programming is simplified since there are no directly associated outputs nor captures, auto delayed mode or external events management. The master timer primarily aims at synchronizing the 5 timing units for converters requiring more than 2 outputs. The 6 events from the master period compare 1 to 4 and the global synchronization are available on all timing units and can be used to set or reset the outputs or reset the timers. The master timer also holds the counter enable bits from all timing units. This allows a synchronized start of all timers with a single write access. Last, it embeds the off-chip synchronization logic programming for interfacing with other HR timer instances in case of multiple MCU systems. have a look at this. Then we will move on to the external events. External events play a key role in HR timer that they dynamically modify the waveforms. Typically to implement a cycle by cycle current control or to restart the counter following a zero current detection. A set of 10 external events which can be chosen from among 30 on-chip or off-chip resources are used to set, reset or toggle the outputs, reset the counters and trigger multiple features such as the burst mode controller, the capture and auto delayed compare, the ADC start of conversion or some protections. The 10 external events are available for all timing units, while the conditioning typically the edge sensitivity is globally done event per event. A different event filtering scheme can be applied to each timer. This raises the external event conditioner circuitry, right, which is a preliminary signal detection stage, which is configured depending on the type of external interface or on the amount of noise and glitches present in the incoming signals. You can see in this figure, the first stage is 4-to-1 multiplexer to select the source, usually an input pin or a built-in comparator. It is followed by definition of the edge or level sensitivity. It must be noted that when the level sensitivity option is chosen, the external events are continuously issued as long as the level is active. Last, a programmable digital filter stage allows removal of spurious transitions at the cost of higher responsible latency due to the filter propagation delay. This feature is available for external events 6 to 10 only. How about event management? In many cases, an active event coming out of the conditioning stage is not necessarily a valid event. So this is typically the case for current feedbacks. The freewheeling diodes recovery current might be a source of spurious overcurrent detection. It is therefore necessary to apply a specific filtering scheme to the external events used in a given timing unit. 3 filtering options are proposed. The blanking mode consists of masking the external events during a defined time window defined within the timing unit itself or using the other timing units. This is typically the case for leading edge blanking. The windowing mode lets the external events go through only during a specified period of time, again defined within the timing unit itself or using the other timing units. An event postpone mode allows an event to be acknowledged and latched only if it occurs during a given time period and delayed to the end of this period. I repeat, an event postpone mode allows an event to be acknowledged and latched only if it occurs during a given time period and delayed to the end of this period. So each of the 10 high resolution timer outputs have 3 configuration bits, isn't it? We spoke about it in our previous sessions. The output is enabled using the OEN bit and disabled using the ODIS bits. All bits are grouped in a single register to have the possibility to enable and disable multiple outputs in a single write access. A disabled status bit ODS indicates if the output was disabled because of a fault detection. The bottom figure is an overview of the whole output stage for a given timing unit. Following the set or reset crossbar, output 1 and output 2 reference signals can first be altered with the push-pull and dead time insertion unit. In push-pull mode, output 1 and output 2 are alternatively in run or idle states. When dead time is inserted, the output 1 signal serves as a reference to the to build the quasi complementary signals, and output 2 signal is discarded. The burst mode controller allows both outputs to be automatically disabled and re-enabled for a limited period of time. The chopper unit can superimpose a carrier signal on top of the active PWM waveform. Finally, the fault stage can disable completely the output to protect the power switches. The polarity is programmed at the end. The entire HR timer waveform can be programmed by just reasoning in terms of active or inactive switches independently from the external gate, driver, and or interface sensitivity before the polarity is applied. Let's look at chopper unit, which superimposes a programmable carrier waveform on top of active PWM signal. A carrier generator is started by incoming pulse and added to the incoming signal by means of an AND gate. You can see in this figure. This allows to interface with the isolation transformer driver without having to add external glue logic. The carrier waveforms can be programmed with 3 parameters. One is the modulation frequency from 1.56 to 25 MHz, and the first pulse length to adjust the settling time, the duty cycle to set the sustained current. So burst mode controller, burst mode operation is of a common use in power converters when operating under light loads. The burst mode controller allows the outputs alternatively in idle and run states by hardware so as to skip some switching periods with a programmable periodicity and length. The burst mode controller can act on multiple timers in parallel. The outputs are disabled simultaneously with a programmable idle state and the possibility to have a dead time inserted upon burst mode entry to avoid any dead time violations. The burst length is programmable as well as the repetition period when the burst mode is enabled in continuous mode. The burst mode can be started on 32 events and it has multiple burst clock options, either coming from the timer rollover event or from independent user programmable period based on the 400 MHz clock. In this example, once the burst trigger arrives, the PWM is active for 3 periods every 8 cycles with pulses skipped for 5 periods. The burst mode controller counter is clocked and incremented on each timer rollover event. If you understood this, go through this, then we'll discuss about fault management. So you should remember the block diagrams I'm sharing over here. Okay. The fault management unit shuts down the PWM outputs and asynchronously forces a user-defined safety state. A software action is required to rearm the outputs. A total of 5 inputs are available, each with a programmable polarity, enable bit, and a digital filter. It is possible to have one fault input acting on multiple timers. For converters requiring multiple synchronized outputs, on the other way around, multiple fault inputs can be merged to protect a single timing unit. The faults are coming from several sources: the digital inputs, the built-in comparators for some channels only, okay, and the system errors. The system errors are indicating a chip level abnormal behavior such as clock security system error, an SRAM parity error, a Cortex M7 core lookup, or potential brownout condition with the PVD detector. This helps to increase the functional safety level. Last, a global output disable register allows all the outputs to be disabled synchronously in a single write access for an emergency shutdown. So numerous fault management options are available, multiple fault protection options. So some are industry standard features. The analog fault uses a comparator. When reaching a user defined threshold, the comparator tripping causes the PWM output shutdown. In digital fault mode, the system is put in safe state when receiving a digital fault trigger. For the cases where one of the output safe state is active, a dead time can be automatically inserted right after the fault to guarantee a safe transition to the fault state without a dead time violation. The HR timer, however, offers some unique protection features. For LLC converters, the delayed idle maintains the current pulse on the output and the fault state is entered only after it is completed. The one marked in the pink. For the push-pull converters, the balanced idle mode guarantees a perfect balance between the two output pulse widths when a fault is triggered before the converter is actually entering the fault state. The output pulse, which is shortened by the fault, is automatically copied on the alternate output before stopping operation. If you understood this, then we can move on to the triggering ADC with HR timer. So HR timer has 4 ADC triggering channels with the 2 channels per ADC for the regular and injected sequences. This allows up to 4 independent ADC processes in parallel for multiple converters. Each triggering channel has 32 sources, including 5 from the master timer, 5 from the external events, and 4 or 5 from each timing unit. It is possible to simultaneously enable multiple sources for a unique trigger. When the various trigger instances are clearly defined, typical in multi-phase converters, as is typical in multi-phase converters. Last, the triggering selection registers are preloaded on the fly. Trigger source updates. Whereas in DAC triggers also offered by the HR timer. This gives the possibility to have a DAC value updated synchronously with the timer update events from the master and the slave timers. This is typically used for peak current mode, where the DAC is used as a threshold for a comparator. It allows the new DAC value, digital to analog converter value, to be applied right at the beginning of the next switching period. 3 DAC triggers are available and it is possible to have multiple concurrent sources for the same trigger. Let's move on to the register update. HR timer. All HR timer working registers are duplicated with a shadow register. This applies to the period and compare registers and numerous other configuration registers. It allows glitch-free operation when updating multiple registers. The write access are done to the preload registers, which are transferred in the active registers when an update event occurs. Usually the beginning of a PWM cycle, at the beginning of a PWM cycle, which we all face, right? 2 control bits allows the hand long of the preload mechanism. A preload enable bit PREN in each timer globally enables the register shadowing. Updates the update disable bits MUDIS and TXUDIS can temporarily suspend the update event for complex HR timer updates or on the fly HR timer reconfigurations. Numerous update trigger sources are available within the timer itself from other timers, master, timer A through E. Other on-chip sources like general purpose timers are following DMA burst mode. The high resolution timer is able to generate interrupts from a total of 85 sources. Here is the listing. They are dispatched on 7 interrupt vectors as follows. One of each timing unit and that master timer plus one vector dedicated for fault management. The table lists all the sources and giving a brief description of each. Please go through it. Then we can go through an DMA request and 77 sources table. This is for DMA. Let's pause here for 2 minutes or a minute or two so that you can go through this. Then we can discuss about low power modes. Low power modes, HR timer can be active only in run and sleep modes. In stop and standby modes, the HR timer must be disabled. That means in standby mode it has to be reinitialized because it is in the power down mode. See, this slide gives a practical use case of the HR timer. It shows how to generate PWM signals for a triple interleaved converter. 3 step-down converters are running in parallel with 120-degree phase shift to minimize the output voltage ripple and to spread the input current demand. They must be synchronized to guarantee a constant phase shift and eventually switch off one phase, adjusting the phase shift to 180 degrees. This is done during the master timer. The events generated on master's period, compare 1 and compare 2 reset timers A, B and C respectively. So the pulse width on TA1, TB1 and TC1 outputs are then programmed using the compare 1 register of each of the timing units as per the control loop demand. If we consider TA1 output, it is built with the output set on master period event. Output reset on timer A compare 1 event. The output TB1 is set on the master compare 1 event and reset on timer B compare 1 event. And TC1 is set on the master compare 2 event and reset on timer C compare 1 event. Note that it is very simple to have an ADC trigger issued in the middle of the pulse width using the spare compare registers in each timing unit. So more related peripherals and resources are RCC, interrupts, DMA, timers, DAC, ADC, documentation and the application note AN4539, AN4885, AN4449, UM1733, UM1735 and UM1736 can help you to understand better in your working stages. We hope we can have a project case comparison in later stages where you will go through, I will explain through all these things in the real time how we are using with Cube IDE, and we may get the outputs in TouchGFX graphics or embedded wizard graphics, which we will be explaining you later. Please like the video if you like it by pressing the like button. If you did not subscribe to our channel and press bell icon. If you think that this is be helpful, please kindly share. Thank you.